Okay, hi. So this is a makeup for the today's class. So I hope the recording is okay. So this is score function. Oops. So we studied, we we proved this, right? So basically, score function is integration of the score is actually I don't know. That is the definition. And dy, dμy, okay. And then we get this one, y zeta, and yeah, I should use this iPad from next class. So this is better. So then we can exchange the order of integration, right? And then this is one. Oops, sorry, one. And so this is zero. So you can see that the real assumption we used, real property that we used is the integration of the density is equal to one. That's almost equivalent to saying that scope function has a mean zero. And we can the same thing on so we can prove. So we proved this already. So we'll just move on. Okay, so here's the message here. Let me insert a new blank. Okay, here. Okay, so the message is that zeta n goes to zeta null in priority. So we studied this already, and we use a subscript so as n goes to infinity. So that means zeta n is a function of zeta 1, zeta n. I mean y1 to yn. So it's a function of n, and we want to increase sample size, then it converges to some true parameter. And now this one, and now suppose you are interested in showing central limit theorem. We don't know. So the problem is that this is a nonlinear function of y1 through yn. So we never really know how to show the central limit theorem or how to compute the variance of the nonlinear function. All we know is how to show it in the linear function, linear sample mean of the IID function. Then we know. So the idea is this: suppose if we can somehow approximate it as a yi zeta null plus negligible, right? Remain the term and negligible. Okay. So suppose we can show that, and then basically the asymptotic property of zeta hat n minus zeta 0 should be dominated by the first term, asymptotic. Okay. And you may wonder what is this a yi? Okay. So suppose we can kind of figure out this linearization and then approximation. Then the idea is y1 to yn IID implies a y1 zeta a yn zeta is also IID, right? This is just a function. So for some function, if you can figure out some function, then the IID, we suppose this is mean 0 y, when mu and sigma square. Then this is IID with mean AY zeta and variance of, so we can basically treat AY as a random variable. That is the basic idea. And furthermore, we are talking about the sample mean. I mean here something, right? I mean negligible. So this is the basically sample mean times square root. So if this is 0, is expectation 0, then we can apply central limit theorem. So because this is just the sample mean of the n IID random variable with the mean 0 and finite variance, then we can establish central limit theorem. So that is what's going on behind this. So basically, basically, if you check this, you can write it as a AYI zeta null, right? Where this A is the term here. So then question is how you actually prove it. Well, there's okay, that uses this Taylor expansion from here. So idea is, if you okay, I'm not sure how much I should, so but I can still try. So summation basically zeta hat n yi equal to 0. And then we know Taylor expansion. We can use Taylor expansion. So basically, Taylor expansion zeta null yi plus round zeta round sample mean of this guy okay times zeta hat minus zeta. And then because this is consistent, so consistent means this will be less than epsilon, right? For sufficiently large n. So that means second order term will be smaller. So that is the basic idea. So that means we can actually kind of do approximation. And then this one is actually really converged to the negative information, Fisher information. So that actually gives you kind of linearization. The null is approximately equal to so you just do it and then inverse and then sample mean. Okay. So that is how we get this linearization, and then basically the variance of variance of then because we know if you apply so you can still write it, right? You can still write it this way. See, so this is what you really want, but this is your scope function. and sample mean of the scope function, and this is just the constant. So we know that this will converge to normal approximately, converge in distribution to normal to to information, right? And then this, so that means the whole thing will converge to normal 0 I inverse times I and I inverse. So that means I inverse. Okay, so that's the final result. So that's the asymptotic, how we usually show asymptotic normality of the MLE. Okay, so that is the about this remark, and but this is not really so. So that basically shows the convergence improperty theorem 2.1 and I think central limit theorem asymptotic normality is theorem 2.2. If you check the book, I have a more rigorous proof, but this is the basic idea. Okay. I think theorem Y, okay, theorem 2.3. Okay. So Bartlett identity, right? Bartlett identity. So point is that, okay, maybe I should write this way. Let me make it more rigorous. So from here, we know that this will normal with the mean 0 and variance I set the 0 inverse and then variance of the S zeta Y and I zeta inverse. Okay. Oops. And then the Bartlett identity basically has a cancellation. Okay. So that is this one. Let me briefly talk about a little bit interesting advanced topic. This is, maybe this is already advanced. So why should I carve more advanced? I don't know, but let's just see whether it's fun to you guys or not. So Kullback-Leibler divergence measure, we already studied this, right? And we already studied, I covered this in briefly because this one is actually constant minus 1 over n log using, right? Using the, so using the model, whatever, if it's parametric model, then this is xi. So minimize of the Kullback-Leibler is essentially, of this Kullback-Leibler is essentially the maximize of the log likelihood, sample mean of the log density. So that's MLE. Now, this is another, so this is more like a projection. So we want to view, so because this is as I said, this is kind of plays the role of the distance, right? So if you have a distance, in a space, some nice space, right, closed and convex and space, like Hilbert space, you have a norm, then you can think of a projection. So the problem is that it is a projection. So you have a baseline. Oops. So you have a Q. So given you have a projection, so this is a L. This is a space of the distribution such that this is the expectation, right? So this is the expectation expectation of the random variable xi, txi, is equal to given alpha I. So that is the space, right? You have a given alpha I, and given the statistics like a sufficient statistic. So this could be like a x or xi square, something like that. So we want to choose a particular distribution function density that satisfy this moment condition, so moment restriction, and with the one outside is q. So this is a density. So this particular distribution does not satisfy this, does not satisfy the moment condition, and then we want to project, right? It's like a linear algebra regression kind of problem. So this is a space of density function satisfying the moment condition, and you want to do some sort of projection, and then the distance here is essentially Kullback-Leibler divergence at q, given q. Okay, and then p should lie here. Okay, so this is a kind of interesting problem. So we call it information projection. And so and because p is density, it should satisfy the normalization density distribution, restriction. And then the solution, so some theory solution is that the solution takes this form. So you can, this is more like a Lagrange multiplier method, because you have a finite, you have a finite constraint, and but the constraint, it has actually integration inside. So that's not simple, but end of the day, what you get is what? Exponential family. So this is more like a baseline. Okay, so Q is a baseline distribution, and then this Q, for example, Q can be, for example, normal 0, 1. Okay, but so normal class, but we want to choose a mean of, right, x equal to a particular number, mu, and variance, so first moment, second moment, mu1, mu2. So if you have this restriction, right, then you want to probably put x and x2 into the space and put a constraint and construct, and then end of the day you will get the solution, which is essentially in this particular case normal, but in general it's an exponential family. So my point here is that the exponential family, why exponential family is so popular? Well, you have a good interpretation as a projection, and based on, so this is a sufficient statistic, and you have you impose a constraint on the expectation of your sufficient statistic to satisfy alpha, right? So there's actually a one-to-one correspondence between the zeta 1 to zeta k and alpha 1 to alpha k. So alpha is actually mean of the expectation of the sufficient statistic, right? That is called the natural parameterization, and then zeta 1 to zeta k is actually the Lagrange multiplier, and that is sometimes called the canonical parameters. But that is more like a purely theoretical, mathematical, or probabilistic concept, not really relevant to our missing data course. But anyway, I just want to introduce, since we already introduced the Kullback-Leibler, I thought that maybe some of you might use why enjoy the powerfulness of the Kullback-Leibler divergence measure as a way to developing the projection in the space of the distribution. So anyway, that's all, and thank you very much for your attention.